the leakage of neutrons from the reactor, but there is a competing effect in thermal reactors. Increasing moderator temperature may increase reactivity, so there is a positive feedback, and at large scale this may outweigh the negative feedback from the leakage. High temperatures compared with light water reactors. Yes, that's true, and advantage can be taken of that. But should we actually be comparing with light water reactors? I should say more about this later when I compare molten salt reactors with other generation 4 reactors, which is possibly the more valid comparison. And proliferation resistance. With aqueous reprocessing, yes, batch reprocessing in particular, you get U232, which spikes the U233 with a highly radioactive component, which would discourage even the most determined terrorists. But pyroprocessing with online continuous extraction of the precursor to uranium-233 can separate it in a form which is easily produced in very pure form. Then you just have to wait and you get very pure U233. So there is a route towards weapons grade U233. The projects considered, they're mainly national or international programs because there has not been very significant investment by commercial organizations, simply because the prospect of significant business appears too far off. So there's very limited information on those small commercial projects. The French research in molten salt reactors, well, first presentation this morning gave a very good presentation of the AREVA position. I think there will be another presentation soon which provides important studies of molten salt reactors and the physics. In particular, the French study had no beryllium in the fuel salts, since it concentrated on fast reactors. So higher temperatures are required because the salt has a higher melting point. The Russian program is probably of limited commercial interest, being aimed more at partitioning and transmutation. There's a significant Chinese program foreseen, but we have limited information on this. We think it's probably thermal spectrum graphite moderated, but it's not clear if it still has high priority. The Japanese program is a long-term plan requiring high technology. The Indian program, we've heard a lot about this. I think there's no need for me to say any more on this. It has potential to be a very large program ahead of anyone else's. The technical concerns. The operation of a historical demonstrator does not ensure current feasibility nor commercial success. Current feasibility, I mean, of a licensable reactor system. The regulatory environment has changed a long time since the molten salt reactor experiment. And commercial success is quite separate from demonstration of a small reactor that was not generating electrical power. Molten salt reactors are not just in competition with current technology, but also with all the other technologies that might come along in the same timescale. So they should be compared with fast reactors, high temperature reactors, everything that is in a relatively long timescale. And for feasibility and regulatory requirements, even as I said, even a small commercial molten salt reactor would be a big scale up from the molten salt reactor experiment at Oak Ridge. So I'll compare molten salt reactor experiments with generation 4. Again, this is the same list as before. The same red marks will come up to show those that are questionable even in comparison or in the context of light water reactors. Then I'll bring up some yellow stars to show points that are not necessarily superior to other Generation 4 concepts. So we've already got these where it's uncertain that thorium molten salt reactors have a clear advantage over light water reactors. High boiling point of molten salt. Well, practically all the Generation 4 systems are high temperature systems with high boiling point coolants. And many of them are liquid metal cooled reactors with melting points far lower than molten salt, so the option of operating at a low temperature, or at least not as high as molten salt reactors have to operate. A broad range of fuel options. Well, yes, you can run molten salt reactors on a variety of fuel cycles. Also, you can with other Generation 4 reactors. High temperatures compared with light water reactors, well, now we're looking at Generation 4 reactors, so it's comparable but not superior. Proliferation resistance, that depends very much on the reprocessing system adopted. And the reprocessing in molten salt allows an opportunity of separating protactinium in pure form and leading towards weapons grade U-233. The materials. Well, Hastelloy N was proven during the molten salt reactor experiment as sufficiently corrosion resistant. But there is a problem. The molten salt reactor experiment did not run for very high power for very long, and it did not really test the embrittlement aspects of Hastelloy N. It actually needs to be modified to reduce embrittlement in the neutron radiation field of the core. And when it is modified, it becomes more susceptible to corrosion. So the operating temperature limits of this material, or the modified form of it, has to come down. That's a problem. The reason that's a problem is that the material has a high, the fuel has a high melting point. Now it has a low upper temperature limit. The opportunities for operating the reactor between an allowable lower temperature limit and an allowable upper temperature limit are being squeezed. There's not much headroom for getting a good temperature difference across the core in, and it becomes worse in fast reactors because the melting point of the fuel salt for a fast reactor is higher than for a thermal reactor. Alternative alloys are under investigation, but this adds to the development cost and to the lead time. The molten salt reactor is definitely not an off-the-shelf option. The molten salt reactor maximum operating temperature is set by corrosion rates and lifetime targets, which does not make it a very hard temperature limit. Transients and brief excursions can go above that and still have an acceptable rate of corrosion. But nearly all the operating time should be below that temperature limit. Above the minimum operating temperature of the coolant, the fuel salt should have satisfactory properties for being pumped around the circuit. Should have reasonable thermal conductivity, reasonably low viscosity, and a fairly small change in the constituency of the fuel can make a large difference to the melting point. About safety, the freeze plug and drain tank combination is generally described as a key feature of molten salt reactor operation as a safety device, but will it work quickly enough? The hottest salt wants to rise, and the freeze plug is at the bottom of the core since it is to drain downwards. So we need to transfer heat downwards, which is not its natural characteristic. Heat wants to rise, so we're relying on thermal conductivity to take the heat down to the drain plug. And if it is a big core to be drained, it needs a big drain plug and big drain tanks. And there is a system there to cool the drain plug, the freeze plug, to keep it frozen, which has to switch off, and then the freeze plug has to melt. This may take much longer than it would have done with the original molten salt reactor experiment. And commercial scale implies increased distance between the core and the plug. For purely conduction processes, timescales are proportional to the square of distance. So a significantly bigger core means a significantly longer time for the freeze plug to activate in a safety operation. Alternatives can work, but are not necessarily passive. They would require an active operation of valves to drain the material, or active valves in parallel with the freeze plug. So the freeze plug is passive if the active system does not work when it should, even if the freeze plug takes longer. Where reprocessing is required, this appears to represent significant technical risk. Concepts of reprocessing systems have been outlined, but only at a rather preliminary level, at least in public. So there's a major development issue there. Development of suitable processes is likely to require investment beyond that which would be supplied commercially. That would need national investment using government funding. There are certainly promising avenues to explore, but they cannot just be declared to be feasible. They must be proven at the required scale in order to provide confidence in the feasibility of the proposal. Proliferation. Well, I've already mentioned this occasionally. It depends on the reprocessing system. The usual claim for safety of thorium and U-233 systems against proliferation is that the reprocessed material is strongly radioactive because of the U-232 impurity and its daughter products. But there are two options there. One is that the reprocessing system might permit pure separation of protactinium, which then produces very high grade U-233 without the 232. The other is that even if the material has 232 in it, there is a reasonably long half-life daughter product, thorium, which can be separated, leaving something that will gradually become more radioactive over a year or so, but can be used for making bombs at least for a short period. And either of those could be a relatively low-cost route to a nuclear weapon. Not practical for terrorists, but they could be practicable for a government for clandestine clandestine removal of weapons-grade material. And pyroprocessing can be performed on a benchtop scale, so it is hard to detect. But as I said, the risk is much less from external access. It has to be an inside job. And commercial considerations. For a molten salt reactor to be attractive now, they must outcompete existing technologies sufficiently that they are worth a significant initial investment. And we've had some presentations pointing out that they are not practicable yet. They need a sufficient quantity of driver material. And safety, well, LWRs are safe, where safe means licensable as safe. And the fuel cost. Uranium is cheap, so why thorium? The answer, of course, is will uranium remain cheap? Operation. Can molten salt reactors follow load with or without grey rods, without excessive temperature swings? Availability. Can high availability be achieved? The impact of refueling outages. Well, that depends on how often it's necessary to shut down for replacing either fuel or moderator. Manning. Can molten salt reactors operate with lower staffing than light water reactors? We don't know this. It's possible. Security. Can molten salt reactors be intrinsically more secure? Proliferation. Waste management. The volumes may be similar or a little greater than from light water reactors, and the very long-term radiotoxicity should be less. Although if you look at the fuel itself, if fuel comes to be disposed as a waste product rather than stored and reused as a fuel, the U-233 itself has a worse radiotoxicity than plutonium, similar in the short term but lasting longer, because it produces several alpha decay daughter products. You get about 6 alpha decays for the price of one, where plutonium would simply go with one decay to uranium-235, which is near enough stable. So, I'll move on to the conclusions. The introduction of thorium fuel cycles may be linked to the introduction of molten salt reactors. In principle, they are a very good combination. Further work is required to quantify the commercial benefits that a realistic molten salt reactor would provide. It's also necessary to confirm the feasibility of suggested molten salt reactor advantages. And concerns must be addressed regarding materials, and especially the achievement of appropriate temperature operation, and safety, reprocessing, and proliferation. Fundamentally, a molten salt reactor must provide some benefit to industry above current technology in order for investment to be attractive. And for molten salt reactors to progress, national programs must develop a concept to the point at which commercial investment becomes viable. At present, there appears to be a very limited readiness of commercial organizations to invest in thorium or in molten salt reactors. Thorium fuel cycles are feasible in light water reactors and liquid metal cooled fast reactors, but in molten salt reactors they are free from cladding material limitations. It's an overall conclusion that no molten salt reactor is yet at a state of maturity sufficient for commercial investment. The present requirement is for support from national strategic development funding. That concludes my presentation. Thank you for your attention.
Jean-Pierre, you have a comment?
Can I comment on the proliferation issue? Because this comes up from time to time. Yes, you can separate protactinium in a molten salt reactor. It's a bit far-fetched. It's rather disingenuous to present this as a new and exciting, shocking discovery. It's been known since the 1950s, as has the countermeasure, the way of blocking this. If you spike the thorium with ionium, which is an interesting element not in the periodic table, it's actually thorium-230, and you get it out of uranium tailings, then that produces protactinium-231, which you then can't get out of the protactinium mixture and goes on to provide the U-232. So yes, there is a rather far-fetched possible loophole in the proliferation argument, but that loophole can be blocked.
Jean-Pierre?
Well, I'm glad that it can be blocked.
Sorry.
But would it always be blocked?
Oh, sorry. I thought it was somebody else.
I wanted to also comment both on the proliferation issue. I mean, in this thermal system, you can easily extract protactinium-233 in almost pure form. So I don't understand the argument we just heard. And the other thing is that thermal molten salt reactors don't address really the issue of waste. And have you given any thought about a fast neutron system?
Yes, from the study we concluded that a fast neutron system, at large scale at least, is probably preferable to a thermal neutron system, but our reason for thinking a fast neutron system would be better is that it would avoid the risk of positive feedback. For waste, yes, we understand that fast neutrons actually reduce waste from other sources, whereas thermal neutron reactors don't. But the thorium uranium fuel cycle does not produce the same higher actinides that a uranium-plutonium cycle does. It's starting further down the atomic mass table, and so it's got a longer way to go. And between U235 and U238, there's a diversion of, there's a low probability of the material going much beyond uranium-235, so it's going, even the equilibrium conditions which are eventually reached would have low concentrations of higher actinides.
Okay, I see no hands. Okay, thank you again.